Hello. This presentation is going to serve as an introduction and explanation of the Newcrom A and B columns, which are a new type of liquid chromatography separation media, developed here at Silk Technologies. This presentation is going to follow this general structure. First, we'll have an introduction into the nature of the Newcrom stationary phases themselves, a comparison of stationary phase interaction with multi-charged ions, and then different examples of the different Newcrom columns used in separations. We will also go over the impact of the organic modifier choice and its concentration, as well as examples of the impact of buffer concentration when all being used on Newcrom columns. And then finally, we'll go over a two-dimensional representation of mixed mode chromatography itself. The Newcrom column series was developed in response to discovered limitations that existed with existing mixed mode stationary phase columns. These limitations were restricted use of methanol in the mobile phase, poor peak shape, low efficiency for multi-charged molecules, the need for high buffer concentration, and poor retention of non-charged molecules. Newcrom columns themselves are mixed mode columns, but they're based on a different type of bonded stationary phase. And the reason for this difference in structure is to overcome the above limitations. This new series includes 4 new mixed mode columns with both anion and cation exchange properties, as well as differing ion capacities. All 4 columns are both reverse phase and ion exchange type columns. And you can see below here, the Newcrom A and AH columns are both the cation exchange columns with different degrees of ion capacity, and the Newcrom B and BH columns are the anion exchange columns that have different degrees of ion capacity. The Newcrom stationary phases are unique in the location of their ion exchange group in the ligand of the stationary phase. A standard cation or anion exchange column has the different ion groups being located directly on the column surface. By comparison, the Newcrom A, H, and BH columns have an alkyl chain that is about 25 angstroms in length, with either their positively or negatively ionized groups located at the terminus of these chains. And the Newcrom A and B columns are a similar structure, but now the alkyl chain is 100 angstroms or so in length, and not the 25 angstroms in length. And the reason for the location of the charge being important is shown here. Most ion exchange columns have the ion exchange groups placed directly or near the surface of the solid support. And this ends up creating a problem with getting uniform distribution of charge along the surface area. This problem does not really exist with singly charged analytes. But when one begins having doubly or triply charged analytes, the degree of uniformity of charge is not the same. Some analytes might be held uniformly, while others might be held only at a single charged site. In a Newcrom column, the charged group is placed at the end of a long, flexible linkage that's far away from the surface. This, in effect, enables uniform interaction between the stationary phase and the charged analytes. So this may not cause much change in the interaction with singly charged analytes, but with doubly and triply charged analytes, the flexible ligands are actually able to bend in shape and reach around the different charged analytes and uniformly coordinate with them at their different charged sites. And this can actually be seen happening on chromatographs themselves. Chromatographs are affected by the placement of charged functional groups relative to the stationary phase. Above, we've shown a standard regular cation exchange column, and below we've shown a Newcrom A column. For the regular cation exchange column, there is no real difference with a singly charged analyte, and the peak symmetry is fairly good. However, with multi-charged analytes, you begin to see a degree of tailing that is happening either at the beginning or at the start, or both ends of the peak signal, leading to very poor peak symmetry. This is due to charge being unevenly distributed along the stationary phase surface. Comparatively, with the Newcrom A column, you can see that with the doubly and triply charged analytes, the peak symmetry is substantially improved than compared to the regular cation exchange column. This is due to the charge being spread more uniformly across the stationary phase surface. On this slide, we are going to show the difference in results when comparing the Newcrom B column to the Newcrom BH column. In the very first example, we're showing the difference in retention times for dodecyl sulfate, which on the Newcrom B column elutes at a much lower retention time than if it were eluted on the Newcrom BH column. The reason for this is because of the difference in the ligand chain length of each column. The length of the ligand chain effectively reduces the amount of ionic interaction that occurs over a given surface area, thus changing the ion exchange retention itself. Similarly, if we look at the example below, we're now separating a more complicated mixture of cationic, anionic, and polyanionic ions. With the Newcrom BH column, we are able to separate out and elute compounds at lower retention times. And on the Newcrom B column, we are able to once again elute out the individual compounds, but compounds 2 through 7 are now eluting at significantly lower retention times due to the difference in ion exchange mechanism, such to the point that compound 8, perchlorate, which is the compound that retains longest on this column, is able to elute in under 10 minutes, whereas on the Newcrom BH column, perchlorate did not elute at all. This is an example that is going to be separating different phosphorylated adenosines. In the above column, we are showing a standard cation exchange column, and below we are making use of a Newcrom BH column. You'll note that all three phosphated adenosines elute at fairly close retention times, and in some cases, such as with the triphosphated compound, there is poor peak symmetry as there is tailing on the end. However, when put through a Newcrom BH column, all three compounds elute separate from one another and all with very good peak symmetry. The reason for the difference in their degree of retention on the column has to do with the degree of ion exchange interaction that they each participate in. The monophosphate, containing the least number of ionizable groups, is the first to elute from the column, followed by the diphosphate, followed by the triphosphate. In this slide, we are showing the separation of different organic acids on a Newcrom B column. These organic acids, shown below, differ in their structures, in their containing of different hydroxyl groups in their alkyl chain, a different count of ionizable groups in the carboxylic acids, and even in the difference in number of hydrocarbon linkages that they contain in their structures. Given that the carboxylic acid groups are the ones that are participating in the ion exchange mechanism, it's the hydroxyl groups themselves that impact the level of hydrophobicity that each compound experiences. This is why glutonic acid is the first compound to elute from this column, as it contains 5 hydroxyl groups in its alkyl chain. The next compound to elute is malic acid, which contains two ionizable carboxylic acid groups and a single hydroxyl group. The next acid is citric acid, which contains only one hydroxyl group, but three different carboxylic groups. Tartaric acid is the next compound to elute. It only contains two carboxylic acid groups and two hydroxyl groups on the chain linkages between them. Malonic acid elutes next, and it contains no hydroxyl groups outside of the two carboxylic acid groups. And then finally, fumaric acid is the last compound to elute, given that it not only doesn't contain any hydroxyl groups, but it also contains now an alkene between its two ionizing carboxylic acid groups, effectively restricting the carboxylic acid groups in their geometry. On this slide, we are showing an example of the separation of neurotransmitters using a Newcrom AH column. The ionizing groups that participate in ion exchange here are the amino groups contained in these three neurotransmitters, each of which differs in their degree of substitution. The remaining hydroxyl groups on the rest of the structure impact the degree of hydrophobic interactions that occur on the column and thus the retention time. As such, norepinephrine elutes first, as even though it contains a primary amine, the three hydroxyl groups contained in the structure, particularly the two contained in the aromatic ring, are interfering with hydrophobic interactions with the stationary phase. The next compound to elute is epinephrine, and this differs from norepinephrine in that the amine is now secondary in nature and is substituted with two alkyl groups. This increases the degree of hydrophobic interactions that are occurring, even though epinephrine contains the same three hydroxyl groups that norepinephrine does. And finally, dopamine elutes last from this column. This is because it has a lower count of hydroxyl groups in the overall structure to interfere with hydrophobic interactions, and this overcomes the now once again primary substituted amino group in the structure. Here, we have shown an example of the impact of the organic modifier identity and the concentration of said organic modifier on column retention. For this example, we're using a Newcrom A column, and we are separating a mixture of different acidic, basic, and neutral compounds under these conditions. In the first example, we are making use of a mobile phase that is 70% acetonitrile in water. Under these conditions, most compounds elute early in the column, with some pore separation later on in the column. However, if the mobile phase is diluted significantly, and now it is 30% acetonitrile in water, there is a substantially greater degree of separation in the different analytes. And in fact, if one makes use of methanol, instead of acetonitrile, still maintaining the concentration of 30% in water, there can be an even greater degree of targeting for the different analytes that one might wish to separate from one another. In this example, we are using a Newcrom column to separate out 4 different alkylated phthalates. But the purpose of this example is to demonstrate the effect of the concentration of the organic modifier on the separation of compounds. Each of these compounds separates out on the column by their different degrees of hydrophobic effects, as they all contain the same substitution but differing lengths in alkyl chains. If one were to try to separate these compounds using a 50% acetonitrile and water mixture, they would find that they would get reasonable separation of each of the compounds. However, if one moves over to a concentration of acetonitrile as 45% in water, the peaks begin to spread out over a greater retention time. And if one further dilutes the acetonitrile to 40% in water, the signals start separating out over even greater retention time, and even the peak symmetry becomes questionable. This is a notable observance in that decreasing concentration of acetonitrile results in longer retention times of analytes, as we can see particularly with analyte 4, dibutyl phthalate, eluting at later and later retention times. This emanates from the increasing hydrophobic effect from the carbon chain ligands themselves. On this slide, we are showing a general summary of the different choices of mobile phase on the different Newcrom columns. We are separating these four analytes, shown down below. And as you can see, the choice between choosing either methanol or acetonitrile can have a great degree of effect on how closely your different analytes elute from one another. In addition, the length of the ligand in your stationary phase, i.e. the choice of do you choose Newcrom B or BH, will also impact how closely your different analytes will elute to one another. The same trend exists with the Newcrom A and AH columns as well. On this slide, we are showing the buffer effect on retention of compounds on two different columns. On the left-hand side of the slide, we have a Newcrom B column that is being used to separate benzene sulfonic acid and benzonitrile. The variable that's being changed here is the concentration of the buffer itself. Benzonitrile retains on the column simply through reverse phase mechanism, and thus maintains the same retention time in all chromatographs. By comparison, if the buffer is greater in concentration and strength, this increases the elution power of the column, and the benzene sulfonic acid elutes at a lower retention time. As the buffer concentration decreases, and thus the strength of the buffer decreases, the benzene sulfonic acid stays longer in the column, and to the point to where it elutes past the benzonitrile. Now, on the right-hand side, we are doing a separation of 4 amino acid-based compounds using a Newcrom AH column. The elution order can be rationalized by both polarity and hydrophobicity. The ionized group here is the amino group in all 4 structures, and the reason for the elution order has to do with the count of hydroxyl groups as well as the placement of alkyl groups with respect to the amino group. The important part here is that if we start out with a 100% water mobile phase with no buffer, we get reasonable separation of compounds, although we get close elution of glycine and alanine. If we begin by introducing buffer, we do keep the same trend of elution, and the glycine and alanine now elute at a slightly lower retention time. But if we start increasing the concentration of acetonitrile, organic modifier, and we keep the increase in buffer, we then start seeing that we can resolve peaks 3 and 4 from one another, to the point of where when we move to a 30% acetonitrile in water mobile phase with 0.1% of formic acid buffer, we can actually have very efficient and substantive separation of all 4 amino acid compounds. On this slide, we are showing a two-dimensional representation of the data one obtains from mixed-mode chromatography. On this graph, on the vertical axis, we have the basicity or the acidity, otherwise known as log D. Over this graph, we have also transposed an ion exchange chromatograph of 7 compounds. When one is close to the origin point of this graph, there is a very low acidity or basicity. On the horizontal axis, we have reverse phase chromatography being transposed. Similarly, the log P is a measure of the hydrophobicity, and so if a compound is close to the origin point of the plot, has a lower retention time, it is less hydrophobic than those that appear farther away. It is possible to take these two graphs and in a two-dimensional axis pattern, graph them against one another, and average the data point wherein different compound peaks should appear. For example, compound 7 elutes very late in both columns, and for that reason shows up much higher and farther away from other data points on the shared axis. Compound 6 shows up in a different location, given that it is very hydrophobic, but not very acidic or ionizable, which is why it does not show up very close to peak 7. This trend follows for all of the other data points. You can then take these points and draw a line towards the diagonal plot that represents the mixed mode column balance of the hydrophobicity and basicity. And in essence, you can now draw arrows from each of the middle points along this line towards their corresponding peaks that would appear in a mixed mode column. These arrows are not necessarily exact with where these peaks show up, but it does help rationalize the order of elution from the mixed mode chromatograph. In summary, mixed mode stationary phases have shown limitations in the terms of the mobile phase additives that one may use to separate and analyze compounds, and also has shown limitations in being capable of efficient analysis of multi-charged analytes. In order to counter these limitations, Newcrom columns have been developed. They are a mixed mode stationary phase column that overcomes these limitations by having an alteration being made in their structure. Through these alterations, analysis is now possible using methanol as an organic modifier in the mobile phase. Efficient analysis of multi-charged compounds is now possible. And the Newcrom stationary phases are available in different ligand lengths as well, giving you yet another variable that you can use to tailor your method for separation of different analytes. And herein, you have the different links that you can go to in order to access any of this information or perhaps further information with respect to the Newcrom column series. We also have the address and contact information here at Silk Technologies. If you have any questions, please feel free to contact us.